Hi, let's continue with the thermal resistant topic. So on the previous video, we talked about how we calculate the thermal resistance of the conduction, and the relationship or the definition of the thermal conduction is the relationship between the heat flux and the temperature difference, as we show here in terms of this equation. So now we're going to go into more detail of the two situations. The first one we are going to address, we call series. So the series is like in the electronic circuit, so which means you have a series of component and put it into a line, so called 串联 in Mandarin. So to compare with the fluid dynamic, we can give an example. In fluid dynamic, if you recall, we have a different diameter of the tubing interconnect with each other. So it's like this. So the length will be different, and the area, or in terms of the diameter, will be different. Then the flow coming from the left hand side to the right hand side. Okay, in this case, we can define the measure loss, as a function of Low's parameter. The D is the diameter of the tubing. Okay, let's write it down like this. Oops. Okay, this we call measure loss. Okay, so it's quite similar in the heat transfer. In the heat transfer, then we put things together like A, B, C, and they all have different K value. Sorry, this B and this is C. Okay, then we eliminate the area, so this will be the small q in, small q out. In this case, the resistance, the total thermal resistance, can be written as such. And you can put it in using a Fourier law. So there will be LA KA plus LB KB plus LC KC. Okay, and this is in the form of the series. And what if it's in the form of parallel? Okay, so in the fluid dynamic, always start with the fluid dynamic. It will look like you have an inlet, and then, for example, it's split into 3 channels. Let's draw it like this. Okay, so it's like this, and then merge back to one output. Okay, let's flow come into the left and to the right, and this path will be called A, middle B, and C. Okay, so the total, the measure loss will be the same because there's a one inlet, one outlet. Okay, so then you can write it down as like this. So FA, LA, sorry, DA, VA square 2G will equal to FB, LB, DB, VB squared 2G and also equal to this. LC, DC, G. Okay, so in the parallel system, the three different paths A, B, C will have the same total head loss. Okay, and in the heat transfer, then you will be like this. Like three parallel, maybe the thickness is different. A, B, C. Then Q is still coming from the left hand side to the right hand side. Okay, then the total R is like the electronic circuits is taken like this. RA, RB, but it's at the down part, RC, and this is here. Okay, so it's exactly like the electronic circuits. Okay, I think it's quite straightforward. And let's take an example. So now we have a composition wall like this, and regardless the area, so that will be small q from the left hand side and the right hand side small q, and that's the three layers, three composition wall, A, B, C, and the temperature. Yeah. Let me write it down, the thickness first. And the temperature profile inside of it maybe look like this, maybe. So because of the K value is the difference, so the slope will be slightly different as well. And the thermal resistance at layer A is defined by the L divided by the K. And don't forget, because here is small q and then here R, we need to time the area back. And then, sorry, RB to LB, KB, A, and RC to LC, KC, A. Okay, so since it is steady, so which means the heat flux propagate between multiple layers will be the same because it's steady. So it's nothing about the temperature profile and the thermal resistance. So it doesn't mean if you have a bigger slope of the temperature profile, then you will have more heat flux in that layer. It is because it's steady, so all the heat flux across different layers, it will be the same. Okay, so the R total here, the thermal resist total, can be written down like this. So we take the area out, it will become LA KA plus LB KB plus LC KC. Okay, and if you are interested in what is the temperature at the interface, then you can do some calculation. For example, let's donate here, maybe it's T1, T2, T3, and T4. Then from the first law, because it's steady, So from the first law of the thermodynamic, then you know the Q equals to Ka, Ka and T1 minus T2. And we put the minus point back into the temperature part, so they will be T1 minus T2. Otherwise, you need to write minus Ka T2 minus T1. Okay, so now I just put it back, the minus, and then make the equation more consistent. Then this will equals to Kb T2 minus T3 Lb. Because it's steady, so the heat flux will across the interface. So it is 3 Lc. Okay, so if you want to know the temperature difference across the first layer, then you can write it down. The T1 minus T2 will equals to, let's put the Q here, and La Ka, right? You just put here and back to another side. And the T2 minus to T3, that's the temperature across the material B, will be Q, Lb, Kb. And similar, T4 become Q, Lc, Kc. Okay, so then if you want to know something like the interface combined with A and B, so for example, the temperature difference between T1 and T3, then there will be something. Let's write it down like this, like the equation 1 plus equation 2, right? Then the Q will equals to like this. Then we'll just combine the layer together. That's quite straightforward. Then if you want to know something, at the left-hand side surface to the right-hand side surface, what's the temperature difference across the composition wall? Then there will be T1 minus T4. Then this will equals to equation 1 plus equation 2 plus equation 3. Then this Q will equals to La Ka Lb Kb plus Lc Kc. Okay, that's what we get. Okay, so as you can see here, we want to know something, the surface temperature on the left hand side and right hand side. Then this will equals to the heat, the small q, and the total resist of your the thermal resistance, and then regardless with the area, and then you just combine them together because it across the material A, material B, and material C. Okay, and one thing to know here with the unit, so we know the K, the thermal conductivity coefficient, is the watt divided by meter and the temperature. And for the convection coefficient is similar, but is the area, temperature C. And for the resistance, that will be from the equation, so the square is on the top, and C divided by W. That will be the unit. Just try to remember. Okay, I can also draw from this one as well. Okay, So this is relatively simple because we put everything into the series. Then if there's something combines the parallel and series, yeah, slightly complicated, but still easy. Let's give you an example. For example, you have a wall look like this. Then start with the material A, and the second layer, you divide by into half. Then that's material B, and the rest of the part is material C, and this is D. Okay, then you have a heat coming from here and coming from the right hand side. And because it's a big Q, so which means we need to consider the area. The area here is A. Here. Okay, and this is LA, and this will be LB or LD because the thickness is the same, and this will be LC. Okay, so from the definition of the thermal resistance, we can write it down. The Q will equals to the total temperature difference divided by the sum of the thermal resistance. So we can write it down again. That is, the delta will become RA plus the R deep, or I write it down in red. BD plus RC. But at this point, this is the parallel. So then you can rewrite it. In this case, the RDB will become RB, RD, like this. Okay, and the rest of it should be relatively easy. For the RA will be LA divided by KAA. This will be LC divided by KCA. Okay, and one thing to address at the RDB, because they share the area. So when you try to write it down like this, the KB, you need to be careful. The area is half. Then this is LB, KD, and half area. Okay, and if you try to draw a thermal resistance circuit, then this will look like, let me put here. Okay, the circuit will look like here. Then you have a Q from the left hand side, and using the conduction into the material A. Okay, and that at that interface and the parallel, some of the heat will go to material B, some of it will go to the material D. So it's like a parallel system, and then link back at the interface, and then connect to the thermal resistance C. So they will be like RA, RB, RD, RC. Okay. So once you draw this kind of thermal resistance circuit, then it will be more obviously you apply the principle from the electronic circuits into the thermal resistance. Yeah, okay, like this. Okay, so now we're done with the custom coordinate. Then we'll look into the cylinder one. Okay, the cylinder one. Let's draw a cylinder first. Then the cylinder. like this. Then you have the inner diameter, we call R1, okay? Then you have outside, you have another layer. Oh, too big. Okay, that's, for example, this is R2. Okay, and somewhere else inside of it, we just define as the R. Okay, so if the temperature at the inner side and the outer side at this point, we call it T1. And the surface at outer surface, we call T2. And these are the temperature here. We will write it down as a T function of R. Okay, so if you guys remember what we're trying to do, dimensional analysis, like a 无因次化. We know the temperature profile at any position divided by the inner temperature minus inner temperature divided by the outside temperature minus inner temperature. This will be the relationship R1 long R2 R1. Okay, that's something we know from the previous chapter. And the heat flux from the inside to outside, the Q, we can use this kind of equation to determine it. So let's do it again, just in case you forget it. Then we become R1 long R2 R1. Okay, so let's eliminate the one we don't need it. So the Q will become like this, and then we'll put the minus into the equation to make things more compact, and divided by long R2 R1. Okay, so that's the Q of it. And how about the resistance? The resistance, we still follow the definition of the thermal resistance. So it's the delta T minus divided by Q. Then the delta T means the inside minus the outside, and the Q at the bottom. Then we just take the Q from here. Then it will become long R2 R1 and 2 pi KL. So this will be the thermal resistance in the cylinder coordinate. Okay, so if we take one step forward, consider you have a multi-layer cylinder. Okay, so in the center we have something called R0. Then you have a different layer. So that's start with this one. Okay, that's the first layer, and the second layer is slightly dense. Okay, and the outer is even more dense. Okay, so you have a different radius. The first one we call R1, the second we call R2, and the most outer layer we call R3. Oh, so in this case, the thermal resistance circuit can be written down like this. So you have the R1, R2, R3. Okay, so the total R will equal to, let's take out the 2 pi L outside. Then this will become long. The outer radius divided by inner and take the value of long divided by K1, the first material of the material conductivity coefficient, and plus the second one, long, the outer diameter, so it's R2 divided by R1, K2, plus long, R3, R2, K3. Okay. So you can see here is always the outer radius divided by inner radius, outer radius by inner radius, outer divided by inner, and then that's the K value of each layer, and you take out the 2 pi L to outside to make the equations more concise. Okay, then you can use the same concept to apply into a spherical coordinate, or we call a shell, because it's we have a different layer of the material, so it's like a shell, 壳状的东西. But I will leave you to read the textbook, and then you can find the similar driving of the equation in the textbook. So yeah, I will leave it like that. Yeah, but we rarely discuss the shell situation. Yeah, because it's not common in real life, and the most applied system actually is this cylinder one, because you can imagine if you have a metal wire in the middle and it's heating up, and then outside you have a plastic cover from it. That will be the multi-layer system, and then this will be a spherical coordinate. So this one is more widely seen in the real life. Okay, so let's take a break.